Before starting with some detailed, with some more general structure, let's start with an example. Consider a 1 plus 1 dimensional CFT with a U1 current algebra. Okay, so let's suppose that the theory as usual is holomorphic. So there is a J and a J bar, and we have J of Z, J of Z, let's say Z1, J of Z2 is equal to, as usual, K left by Z12 squared plus regular, and J bar of Z1, J bar of Z2 is equal to K right, okay, Z bar 1, 2, the whole thing square plus regular. Okay, now the question we're going to ask is the following. Suppose we take this theory and couple it to a background gauge field. Okay, so we couple it to a background gauge field. Let me see Polchinski's conventions. Yeah, so suppose the coupling is Jz Az bar plus Jz bar Az. And we add this coupling to the path integral. Then we integrate out all our fields. Our final answer is some number, because it's a partition function, but it's a number that is a function of of Az and Az bar. Okay? And the question we're going to ask is, what is that number? What is that partition function? Well, let's just work quadratically in A. Actually, the answer we get will be valid for more than quadratic, but not important for what I'm saying. So let's just work quadratically in A, in the exponent. So that, of course, now is very clear, because the terms that are quadratically in Az bar are the coefficient of that is the 2-point function of Jz, which we've listed here, right? And the term that's quadratic in Az is the 2-point function of Jz bar, which we've listed here. So up to quadratic order, Z of A is equal to integral Az of Z1, Az bar of Z1, Az bar of Z2, K left by Z12, the whole thing square. Okay? Plus integral K right Az of Z1. When I say Az of Z1, this could be a function of Z and Z bar. I'm not writing that explicitly. Like Z, Z1 bar. It's not necessarily analytic. J might be analytic. That's a dynamical statement. But my source is just any arbitrary function. Okay? And Az of Z1, Az of Z2, again, Z1, Z1 bar, Z2, Z2 bar, Z1, 2 bar, the whole thing square. Okay. Now all this is very good, but there's something a little puzzling about this answer. And the thing that's a bit puzzling about it is that we had expected, we have this general naive argument, right? That if I take integral J mu A mu and my current was conserved, was genuinely conserved, okay, then the final action will be gauge invariant under A mu gauge transformations. Why? Because delta of this will be equal to J mu del mu phi. Then you integrate by parts, which is minus del mu J mu phi, and that is 0 because del mu J mu is 0. Okay, we're dealing with a conserved current because Jz is analytic and Jz bar is anti-analytic. So if we were looking at things that are first order in A, It would definitely be conserved. But now we're looking at things that are second order in A. The question we're asking is our current conserved even in the background of an A field? Are the terms in the conservation of the current that are first order in A themselves 0? That is not completely obvious. Okay? So the kind of question we're asking, an equation we could imagine is del mu j mu is equal to number times star of f. This should be consistent with everything we know, because when f is 0, del mu j mu is 0. But when f is non-zero, it's not 0. That's possible. Okay? So the question we're asking is the action genuinely gauge invariant, okay, as a function of z, as a function of this background gauge field A, when I do a gauge transformation up to this order in the A expansion? Is the question clear?
What is the difference between this lower line and the upper thing? That when it's an action.
If del mu j mu was 0,
Yes.
as an honest operator equation was not something like this, then we would get 0.
Yeah.
Suppose del mu j mu was this, then instead of 0 what we would get is minus star f times 5.
Yeah, but I'm saying that doesn't the lower line follow that the top line will also be automatically invariant? Because top line is something that we got by integrating this thing. When I add j mu a mu term to the action,
Yes.
I do the path integral.
Yes.
I get the quadratic AA form, which you have written upstairs.
Right.
So if this statement is true, then somehow the top statement also
Should be true.
Yeah.
So the question is this statement true? Now we're going to check it using the top statement. We don't yet know. Okay? Now, first we'll do some algebra, then I'll say some words. The algebra is the following. So what we have to do is now make a gauge transformation. Okay? So let's suppose we make a gauge transformation. Okay, so let's say I make a gauge transformation with the field phi. Okay, and let's compute how the action changes. Okay, clearly the two guys are on equal footing, so we'll get twice the change when it acts on any one of them. Right, because z1 and z2 are integrated over all z1 and z2. Okay, so clearly the change in the action will be proportional to del s is equal to KL A mu bar, A z bar z1 del z bar of phi, okay, 1 by z12 the whole thing square, z bar 2 of phi, 1 by z12 the whole thing square. This is at z2 and d2z1 d2z2 plus k right and something similar. Okay, I'm just writing here, we'll fill it in later. Is this clear? There's actually a factor of 2 which I'm not keeping track of, because you could have had the gauge transformation act here or here and you get two terms, both of which are the same, because it's just a dummy variable. What? This is 5z2. Oh, I wrote 1, sorry. Thank you.
then quadratic term, right? Which just pure means.
But I'm working infinitesimal gauge, infinitesimal variation. Right, we could do more. Okay. Okay, very good. Okay, so now let me do now let me take this and integrate by parts. Okay, so what do I get? Well, when I integrate by parts, I get the following. I get KL. So there are two terms that this thing could hit. Well, I could get del z bar. I could have the z bar hitting this, or the z bar hitting this. Okay, let me look at both those terms. Now, actually, sorry, I said it wrong, because this is a function of z2 and this is not a function of z2. As far as the z2 integral goes, z2 appears only here. Okay, so delta s is equal to, okay, let me just be sophisticated and put a 2 here. Okay, and then I'll be even more sophisticated and I'll put a minus because I'm integrating by parts. Okay, and we will get integral az of z1 del z2, z bar 2 of 1 by z1 to the whole thing squared, phi of z2 d2 z1 d2 z2. And then something similar from the anti-holomorphic. Just work out holomorphic and then I'll write down the anti. Was that clear? Now we can write this as del z2 bar of 1 by z1 to the whole thing square.
As minus of del z1.
Exactly. As, what I'm going to do is minus of, this is del z1,
Z1, yeah.
del z2 bar of 1 by z1 2.
Yes.
Right, because the
Yes.
minus del z1 makes it z12 square.
No, just.
Did I get a minus?
No,
one?
actually, this should be. I mean, del z bar 2.
I've-
If actually hitting on that should be. If there has to be some bar in. I mean,
This is the
some
bar.
mod square. Or would it? Sorry.
No. See, all I'm doing is writing 1 by x square is equal to.
Yeah. That step is okay, but no, what I'm thinking of is that del z bar 2 hitting on that should be identically 0.
Not quite. It's a delta function.
Oh, right. Yeah. Yeah, okay.
That's why I
Del
pulled out
Z1
one.
of del, yes. Yeah.
Okay, and this is equal to. We should get the factor right. Some pi.
Yeah, I mean, yes, sometimes the delta function, moving the derivatives back and forth could be a little subtle, right? I mean, but here it does not probably.
Yeah. Yeah. I think we could do it more seriously.
I see. Yeah, I mean, but yeah, I mean,
Yeah.
because it's.
Well, let's see. Am I doing
I
anything?
mean, I was just wondering
think-
if there could be any subtlety in.
Well, I think the del z can move through. It's the del z bar that.
Yeah.
Basically, the statement is that this is derivative of delta.
Yeah, so what I'm thinking of is the del z bar when it hits on 1 over z, it's obviously delta function. But if I write some 1 over z squared, del z bar on 1 over z squared is 0.
Oh, no. It's not. Let's check.
Okay.
Let's try to understand why is del z bar of 1 over z a delta function. Let's give a good proof of this. Okay, let's see. So the claim is that this is an aside. We want del z bar of 1 by z. We want to claim is equal to delta
With some.
with some pi or something. Let's do it seriously so we figure out the number as well. Okay, delta 2 of z. This is the claim. Now, if this is true, if this is true, it must. What this statement means is I take any function of phi of z bar, del z bar times 1 by z. That must be equal to pi times phi of 0.
Yes.
Right, if I'll put some number. Now, the way I'm going to work is this. Let's see. What I want to do somehow is to use Cauchy's. I want to take this dz bar integral and do first the z integral and then the z bar integral. Just give me 1 second. There should be some you know, I'll tell you what the spirit of the argument, I would have to get it straight. But I think the spirit of the argument is this. You take this two-dimensional integral and break it up into a bunch of contour integrals. Okay. Now, what? I could do that, but I wanted to give a more beautiful argument. It's something about, you know, either the contour captures the pole or it does not. And this del z bar will be like moving the contour. So it's the difference between capturing the pole and not, is what I feel. And that will give you a difference of pi or 2 pi or something. Give me a minute, or maybe I'll try to sorry. No, later.
That's too much of a...
Yeah, there is a nice, it's actually a useful exercise, but we'll do it later. We'll just take too long. There's some clean way of arguing this thing. But and the thing about it is that if you do the same thing with the z bar, you would have to go to one higher order in the Taylor expansion here. This thing will only keep phi of 0, but you'll have to make this actually the pole to use Cauchy's theorem. Okay? Yeah. And that will pick up the derivative.
Yeah, it's a
derivative of
delta
delta.
function.
Exactly.
Yeah, that's okay.
That's how it will work.
Yeah.
But I'll give you a clean argument at some point. Sorry. I would have to reconstruct it. I'll do it at some point, but okay, fine. No, but I think this is okay. Fine. Now this, up to some pi and so on, the only thing that will matter for us is relative factors. So up to some pi, let's declare the number pi is minus del z of pi times delta of z12, delta 2 of z12. We could easily work out this factor correctly using Stokes' theorem, right? Like this we've done before when we worked out the Green's function for the massless scalar field. I'm not bothering to do it. Just it distracts us. Okay. So then what we get here now, because of this del z, now this was a del z1. We take that and integrate that by parts here. So this it doesn't hit the phi z2 because that's z2. So we get del z az times pi of, but now z1 and z2 are forced to be at the same location because of the delta function. Okay, so up to some sign and maybe some factor of 2 and so on, the answer is clearly del z az times phi of z times phi of z. Because what was z1 now we call just z because there's no name, there's no 2, because we've done the delta function integral. Right? That clear? Okay. And we get something very similar for the, in fact, yeah, Pulchinski, when he did it, he got a minus pi. Okay, so I'll put a minus pi. And you get basically the same thing from the...
Just one more thing, look, so initially this AZ bar was a function of both Z1 and Z1, okay,
bar.
Bar, so when we shifted to the Z2 bar, it was, we were doing it in an order so that it hitting on that gave 0. That it was not formally a function of Z2.
It's not a function of Z2, there are 2 points, 1 and 2.
Yeah.
It's not a function of where 2 is, it's a function of where 1 is. So when you change 2, it doesn't change, right? Right? And then we get basically the same thing from the other side. So plus KL into this plus KR into del Z bar AZ bar phi of Z. Okay. Now, this is how this path integral changes under the gauge transformation. and it just does not look gauge invariant. However, notice something. So we'll look at it a little more. But however, notice something. Suppose KL was equal to KR. Suppose. Then this thing becomes is equal to minus pi integral k. Let's say is equal to k. Del z az phi del z az plus del z bar az bar phi. Okay, which is equal to minus pi, so plus pi k into az del z phi plus az bar del z bar phi, which is equal to pi k times delta of az bar. Right, because under a gauge transformation, Az changes by del z bar. Which way?
Yeah,
right. Did I get these right?
this is right.
This is right, yes. Wait, no, but wait.
This is high.
Have I been messing up my z's and z bars? Just a minute. Yeah, there's no z bar. Oh,
No, this comes from the second anti-holomorphic.
yeah. You just wait. I'm getting a bit just a minute. Just a minute. Yeah, it's fine, right. I'm sorry. I was just, what am I saying? So, what? Is that del z bar?
It changes by del z.
Correct.
Then it will be opposite.
It's opposite, right? So yeah, what's going on here? Did I do this algebra right?
AZ bar.
It was az bar. Yeah, I messed up something. I'm sorry. This was bar, right? Yeah. Thank you. This was az bar and this was az. Thank you. Now it's correct. So this was az bar, this was az, and then it's really that. This was del z az bar, del z bar az. Sorry. Okay. Now you see that in this case, what I can do is the following. If I define my z to be this quantity here, then it's not gauge invariant. Okay? But suppose I define z prime equals z times e to the power minus pi k az bar dz d2z. Suppose I just define that quantity. Yeah, I'm just multiplying up in the exponent, right? So
And
subtracting in the exponent.
Yeah, and which corresponds to adding a non-gauge invariant term to the action.
Which corresponds to adding a non-gauge invariant term to the action, which is chosen precisely so that its variation
is gauge invariant.
cancels the non the gauge variant term of the path integral. Yes. So z, the change in z. So firstly, z was e to the power. So this is log z.
Yeah.
Right? Log z is this, perhaps with some sign. Okay? Now the change in log z is simply the change in this object. So if I just add this object to my original action with a minus sign, that will cure it. Notice that this here didn't involve the dynamical fields of the problem. It just involved the background gauge fields. which were numbers. What is this saying? This is all, and notice also that this is a local term. Right? This is AZ bar at the same point. So by adding this to my definition of the theory, what am I doing? I'm not changing 2-point functions of currents at separated points. Because this addition changes only contact term contributions in the current 2-point function. All I'm doing is changing current 2-point functions at exactly coincident points. Okay? By changing my definition. Now you see, this is exactly what happens when you change a regulation scheme. You change in one regulation, the difference between working in one regulation scheme and another regulation scheme is a purely short distance effect. So it gives you purely local contributions to correlation functions. Changes contact terms basically. So one way of thinking of it is this. I was working in a regulation scheme that did not preserve gauge invariance. But in the case that KL was equal to KR, that was fine because I could just change my regulation scheme or work in the same regulation scheme and just by hand add this non-gauge invariant term to the action, so that the whole answer is gauge invariant. Is this clear? So in the case KL is equal to KR, there is a way of changing the definition of the theory in a purely local manner. That's in a purely local manner.
I mean, what is
There's a way of changing the definition of the theory.
Okay, in a purely local.
In a purely local manner, so it doesn't affect correlation functions at separated points. To make the theory gauge invariant. Basically, it's a choice of regulation scheme. Okay?
Can you say why this term only affects the short distance?
Because now let's compute the 2-point function. J of Z1, J of Z2
Oh, it'll be just differentiation
with respect to this, and it's at the same point. Okay, so it only affects things at coincident points. Clearly, that's a very singular thing to do in a quantum field theory, right? Like, the same point is a very strange kind of thing. If you think about all the analysis we've done about conformal field theories, all our correlation functions are always valid only at separated points. We try to stay away from what happens at the same points. These counter terms are things you try to stay away from. You're saying you can fool around with these counter terms that give definition to the theory in a way to make it gauge invariant. That is fine. But nobody told us, there wasn't a God-given regulation scheme to work in. We can choose one and make it gauge invariant, we're happy. Okay? So what we conclude is that when KL is equal to KR, the theory is actually physically gauge invariant. Okay. Now,
So I was just wondering, can this extra term be thought to arise from the Fujikawa trick?
it can. That would be another way of doing it.
I see.
Wait. The term that is the problem when KL is not equal to KR.
No, when KL equals KR.
Yeah. When KL equals KR, if you use a good regulation scheme and you use the Fujikawa trick, you won't even see a problem.
Okay.
When KL is not equal to KR, there's a problem, and you will see that problem from the Fujikawa trick.
I see. And this term would roughly correspond to the change of the measure of the path integral.
This term is nothing. This term is working in a particular regulation scheme,
I see.
okay, which you wouldn't even see in the Fujikawa trick. It's only when okay, we'll come to some of this, right? Okay, excellent. Now there are two more things I want to say. The first thing is this. Look, we said what we needed to add to the action to make it gauge. Let's first work with KL equals KR. Then we go back to KL not equal to KR. Okay, so when KL was equal to KR, what was our action? Our action was D2Z1, D2Z2, A Z bar Z1, A Z bar Z2 by Z12 squared, k outside the whole thing plus az z1 is z2 by z12 bar square. Okay? But now we've changed the definition of our action. Okay? We've changed the definition of our action so that, okay, now I'm using Polchinski's factors, okay? Right, that half was because we would have got the 2 otherwise. Okay? And the subtraction is, I hope I'm getting the, yeah, right, with a minus sign. So now the actual action is this minus k integral az pi integral az bar d2z. Right, because this is the extra term we added. This was the term we claimed. So let's take a k by 2 out of the whole thing. So I'm getting rid of this now. The integral is there, we understand it, so I'm writing this as k times this, k by 2 times this, plus 2 pi times this, minus 2 pi times this. Let me put that there. This we claim is a gauge invariant answer. We checked that gauge variation vanished. Okay, this was a double integral over z1, z2, and this is a single integral only over z. Okay, now why is it gauge invariant? Well, one way of saying this is the following. This I'm claiming is the same thing as the following term, k by 2 integral f z z bar z1 f z z bar f z z bar z2 f z z bar z2 log of this is the claim. Okay, let's check this claim. Okay, so let's check this claim. So the basic point is we're going to take these, expand it, and integrate by parts. Okay, so this is k by 2 del z az bar minus del z bar az at 1 log of z12 the whole thing squared times del z az bar minus del z bar az at 2 at z2. Okay, now you see we're going to get two kinds of terms. First term will be where you take the del z from here and the del z from here. When you do, and we'll integrate both by parts. This will give us a 1 by z12 squared. That term will become this term.
Yeah. Oh, I see.
Then there's a term where you take the del z bar from here and the del z bar from here.
That will give a delta function.
No, when you take two del z bars, that will give you this term.
Yeah.
Exactly.
One z and one z.
But when you take one z and one z bar, one of them will give you z12, and then you get del z bar of 1 by z12, and that will be the delta function. There will be a pi. There are two such terms. It will become a 2 pi, and so that will give you this term. Okay, so I'm not working out the algebra more than this, but it's very plausible that it works. Okay, so in the case that the thing was gauge invariant, in fact we got the answer. What is the answer for the partition function at least a quadratic order in F? Okay, what is the answer for the partition function at least a quadratic order in F? Or a quadratic order in the gauge field? We've got a very beautiful answer. The answer was field strength integrated with a log. Okay, and in this form it is manifestly gauge invariant. Now there are two things I want to say about this. The first thing I want to say is the following. Notice that the answer, either the one above this part or this part, is non-local. It's not a product of some local expression. If it had been local, it would have meant that correlation functions of j's at unequal points would vanish, which is crazy. Right? So clearly we expect a non-local answer. Nonetheless, the variation of the action under gauge transformations was local. Why was it local? It was local because the answer, the action classically was gauge invariant. Okay, so suppose this was like a chiral boson, for instance, or something. Something with a U1, some obvious U1 symmetry. Classically, it has this symmetry. The only issue is one of regulation, right? This is always the case with anomalies. Regulation can take what is an obvious classical symmetry and make it not a symmetry. But regulation is a short distance effect. Short distance effects should only show up locally. So it's a general thing that while the action as a function of gauge fields is non-local, the general expectation is that when you take it and vary it under a gauge transformation, that variation will be local. Because it's a short distance effect. It cares only about what happens at very short distances, therefore it should be local. Right? It's a regulation effect. It's what happens when you take your lattice to 0. Okay? That we've seen illustrated here. We just did algebraically, but we found this general phenomenon. Now, the object, the local variation that we got, the fact that the variation was local was not enough. Not every local variation is the variation of a local counter term. When we had a local variation that was by itself the variation of a local counter term, that was not an anomaly because we could just add that counter term to our action and remove that variation. So we could define a quantum field theory correctly with the right choice of cutoff, right choice of regulation, so as to make it non-anomalous. Those variations that are not the variation of a local counter term are obstructions. They genuinely cannot be removed from the theory. Okay, and they are what you think of as an anomaly. Okay. The last bit of algebra I wanted to do with this problem was the following. Let us take this quantity here and try to understand. Go on.
Maybe this is a confusion, but we started with defining this correct algebra and OPs of J's and J bar. That does not directly imply that del mu of that thing is 0.
It did when there was no background A.
I see.
Okay.
But then if I just write it in action as a coupling term of A and J, and if I do a gauge transformation, then it'll give me a del mu J piece by.
Yes. So if you kept del mu J without keeping terms on the right hand side that are also proportional to A, you're fine. The problem is terms proportional to A, right? So the current was conserved in the absence of a background gauge field. The question we're asking is, in the presence of the background gauge field, this is still conserved. Okay. Is it clear?
Yeah.
Okay? Okay, so let's answer that question more quantitatively. See, we had this this term here, this was the variation. And in the case that KL was equal to KR, we subtracted out this piece. Okay, so let us try to do the best we can, even when KL is not equal to KR. So do some sort of subtraction, make this look as nice as possible. Okay, it's got to be a subtraction that's democratic in LNR. It has to reduce to the one that we have when KL is equal to KR. So basically we replace K by average. So let me see. Did we keep track of the signs correctly? We had minus, then we made this plus because we made it del phi. Fine. So we wanted minus pi KL. So the variation delta S or delta log Z, Z prime is minus pi del Z A Z bar phi plus KR del Z bar A Z phi, and then let us put minus KL plus KR by 2 delta of this quantity. So let's put the counter term to be KL plus KR by 2 with this quantity. I hope I've got the sign right, otherwise I'll correct it. Minus del Z phi AZ bar plus del Z bar phi AZ. Okay. And now let's collect terms. Okay. I hope I've got all my factors and so on right. Let's collect it. Sounds more or less okay. Let's collect terms. So we have phi times, let's integrate this by parts. So that's plus phi times dz az plus phi times dz bar is z bar.
Individually multiplied KL and KR to the first and second term, so that when you partially integrate this clubs with the first term and second term.
Sorry, say again.
If you individually multiply KL to the first and second, then the partial integration will club with the.
You want to kill these terms. No, but that we're not allowed to do, right? We're only allowed to add a local counter term.
Yeah. So I'm just saying, first term, right, rather than writing KL plus KR by 2 outside, just multiply first by KL and the second. Oh, that we can't do. Sorry.
You're not allowed to do that.
Sorry.
Yeah. We need a minus sign. Let's take a minus sign. Yeah, what I want to get is a field strength.
Both terms will give KL minus KR with a sign.
Exactly, that's what I want. That's coming.
This way it is.
Yeah. So del z az bar. So we get del z az bar minus del z bar az
With a phi and KL minus
with
KR by 2.
phi and
some
yeah.
Overall sign.
KL minus KR by 2 and some pi or something like that, right? Something like this. Okay. So this is integral of integral of f times phi times KL minus KR by 2 and some pi's and so on. Right, Again, think of this as a 2 form, we're integrating it. Now, what did that mean? You see, as we did right in the beginning in our naive manipulation, suppose we had integral j mu a mu, maybe j mu a mu, and we did a gauge transformation. This is going to be interpreted as del mu j mu times phi. So we can read off the coefficient of phi as effectively del mu j mu. Okay? So do you say that what we're getting effectively is del mu j mu is equal to some number which is proportional to kl minus kr and then some pi's and so on times star j as star f. I mean, the fact that there's a star is simply the point that here I was doing a form kind of integral, there I was doing a scalar integral.
Yeah.
So form integrated over a manifold is same as star of that form integrated like a scalar. Right, so that's, so to compare the two.
Form is same as in the dimension.
Higher, yeah, is top dimension.
Yeah.
Right. Okay, so you can do this all more carefully. But the point I wanted to make is that this calculation not only tells us that the theory is non-anomalous when KL is equal to KR, it also gives us a formula for the anomaly. It tells us that del mu j mu is equal to something very specific. You know, when we varied the action, okay, when we varied the action, we ended up with something very specific. Is this clear? Just by comparing the first order variation. Now, you know, actually in this theory, there is no other term that cannot be removed by local counter terms. I will try to give you an argument. It's just a dimensional analysis kind of thing. That the only obstruction is at linear order in F. The general rule is that the obstruction in d dimensions is of order f to the power d minus 2 by 2. I mean, has d minus 2 by 2 f's. Did I say that right? Sorry, I said it wrong.
4D it's f.
It's 2D, it's f. It's a d by 2, sorry, not d minus 2, d by 2. In 2D it's f, in 4D it's f square, 6D it's f cube, and in 10D it's f to the 5, as we will see.
And this is a one loop exact statement.
This is a completely exact statement. I will try to tell you the structure of this in a little more detail.
All other orders
Can be removed. There is no other obstruction other than this. So even though we only looked at this, it's actually the exact thing. Okay, it's you know, well, I will try to explain this. I will try to explain this to you. Okay. Okay. Though you're right that as our calculation has only shown this so far, but it's actually something exact. Okay. Fine. There is one other thing that I wanted to point out about the answer. Okay, and that other thing that I wanted to point out is this. Notice that in this case, if I did a second variation, go on.
We compared modified action, right?
Yes.
The modified action with the counter term added.
Yes.
And should we compare the variation of the modified action with the counter term added also? When you say J mu, should you add the counter term?
No, that's now a definition of J. Whatever our definition of J is. Our definition of J is variation with respect to A. So J is now being defined by the modified action. So we're correcting the definition to make it as good as possible. Is this clear? Okay. Now notice there's one other thing, that just like in the gauge invariant case, we corrected the definition to make del mu j mu 0. So we had to change the definition of j in order to make that 0. Here we changed it to make it as nice as possible. Okay. Now, perhaps the last thing I want to say about this calculation is this. Notice that if I may, what we found was that if we made a variation with phi 1, with some field phi 1, okay, we got k1 minus k2 times some number which I'm not keeping track of, times integral f star phi star f d to z. Now, if I take this and I vary with respect to phi 2, I do a second gauge transformation of log z. So this was equal to this, and therefore del phi phi 2, okay, del phi 1 of log z is clearly equal to 0, because the variation, because the first variation, okay, the first variation gave us something gauge invariant.
I mean, it's not even the commutator,
that itself is 0.
So the ways dominion consistency.
Which is what we're coming towards. So in this case, because this is 0, it's also true that the del phi 1, del phi 2 of log z is equal to 0. These are trivial things. But in particular, it is, as Upmanyu noticed, it's del phi 1, del phi 2, or maybe del phi 2, del phi 1, minus del phi 1, del phi 2 of log z is equal to 0. Obviously, since each term was equal to 0. But this, we could have argued from before, had to be 0. Because you see, what we are doing is taking some quantity and then varying with respect to phi 1 and phi 2. Now, in this case, we were doing some abelian operation. You do a gauge transformation with respect to phi 1 and then with respect to phi 2, or you do it in opposite order, you get exactly the same thing. Okay? So this, just from the algebra of gauge transformations, no matter what log z was, had to be 0. Now, let's say that this quantity is the quantity we call the anomaly. The coefficient of phi 1 in the variation of log z with respect to phi 1. Let's define that quantity as the anomaly. Okay? With that definition, this turns into a non-trivial statement. At this level, it was obvious, right? I mean, by the way, here we use that we were using an abelian gauge transformation. If we were doing some non-abelian gauge transformation, we'd get some FABC on the right hand side. But anyway, we'd get a clear algebra. Okay? At this level, it's obvious. It's some obvious statement. But you see what? If we somehow know the answer just for this, or somebody wants to give us a guess for the answer for that, then this becomes a non-trivial statement. Okay? Because it tells us that, let's call del phi 1 log z equals a1, which is equal to phi 1 times whatever. Okay? And del phi 2 log z is equal to a2. What we find is del 2 a1 minus del 1 a2 has to be equal to 0. So since it's a1 that appears on the right hand side of the del dot j equation, all possible terms that appear on the right hand side of the del dot j equation, they're not completely arbitrary. They have to obey an integrability constraint. because they came from varying something. Okay, that this integrability constraint is the same as del x del y of some quantity. Del x of del y is same as del y of del x, that basic kind of thing. Okay, or some non-abelian version thereof. Okay, in our case it was trivially satisfied, but more generally the description of anomalies uses this fact in a highly non-trivial way. Okay, so that's all I wanted to say about this more or less. It is non-trivial when you have non-abelian. We'll see. Yeah, right. It's most non-trivial when you have non-abelian symmetries. Okay, exactly. Fine. Any questions or comments about this? By the way, about a year ago in our class, I don't know if you remember it now, but we argued that when CL was equal to CR, we found a clean answer for the partition function of the conformal field theory as a function of the background metric.
Yeah.
But when CL was not equal to CR, we got no answer, because we got one answer from CL, another answer from CR, and we didn't know what to do. That is basically the statement that we had a diffeomorphism anomaly. That there was no consistent way to couple our field theory to an arbitrary background metric. Okay? Well, you can rerun all those things in this language. Okay? It would tell you that in such a theory, there would be del mu t mu nu would have something non-zero on the right hand side involving some curvatures, if CL is not equal to CR. Okay, I'll leave that for you as an exercise. Such things are called gravitational anomalies. They're called gravitational anomalies because if you took that symmetry and gauged it, what you would be doing is gravity. Okay? And a theory can have mixed anomalies. What does that mean? It means that if I have many symmetries and I compute d mu j mu, I vary with respect to one of the symmetries, I could get something non-trivial in a background gauge field of the other symmetry. Right? We are dealing with theories such that when all background gauge fields are 0, del dot j is 0, or the variation of the action is 0. But when you turn on background gauge fields, del dot j may or may not be 0, which is equivalent to the statement that the variation of the action may or may not be 0 for terms proportional to other gauge fields. Okay? Now, it's possible for a theory to have a mixed anomaly. You could have del dot j is not equal to 0 because of the background curvature. And indeed we've encountered examples of this sort.
What is this mixed anomaly?
Mixed means
Multiple symmetries.
exactly. What we did here was to take a particular symmetry, turn on a background for that symmetry, and vary with respect to that symmetry. So we got del dot j is equal to the field strength corresponding to the same symmetry. But it's possible that you have two different symmetries in your game, symmetry 1 and symmetry 2, and you get del dot j1 is equal to field strength for symmetry 2. Okay? So this is the statement that symmetry 1 is not, the current corresponding to the first symmetry is not conserved in the presence of the background gauge field for symmetry 2. Such things are called mixed anomalies for obvious reasons, right? You don't see the problem unless you deal with two symmetries separately. Okay, now we have seen an example of such a mixed anomaly in our discussion of string theory. Can anyone remind me what it is? Okay, to save time, I will tell you. It's ghost number current. Do you remember that we saw that in the JG, I can't remember, T of Z, JG of 0, this was not a primary operator. This had a term which was some number by Z cube. Do you remember that? In fact, we did this calculation. You probably remember when we computed del mu J mu, which is dz bar jz for this ghost thing, we got something non-zero proportional to r. And then we integrated that over the genus G Riemann surface. And we used that to deduce that the number of zero modes of the B0 modes minus C0 modes was related to the genus of the surface using the Riemann. This is exactly a mixed anomaly because it's the divergence of one current, namely the ghost number symmetry current, okay, is non-zero only when you have a background field corresponding to some other current, namely diffeomorphisms. Turned on. Had you been just in flat space, it would be conserved. Here it's not. Okay? It's typically true that, well, it's always true in conformal field theory, that if you have a current with the stress tensor and you have a 1 by z cube term, that signifies a mixed anomaly between diffeomorphisms and that particular current. Okay, if it's lack of being a genuine primary operator signifies a mixed anomaly. And fine. Okay, we could say more about such things, but let's move on. Any questions or comments about this?
Is there some relation between this anomaly being some sort of curvature of the couple background?
I didn't understand the question. Say again.
In this sense that I mean it's star f here, right? So we can see that if I decompose on equation function and do a y transformation on my background, this thing, I'll get box 1 over r box now. So I mean these terms, anomaly terms, seem to be only related to the curvature of these couple fields. Like it's f here is r.
Yeah, you're asking will it always be true that anomalies will be related to curvatures of background fields? That's the analysis we're going to do now. You'll see, more or less. You'll see. Okay. Now what I want to do is to give you. So what we've done so far is to take one example and sort of kill it. Okay, but the world is full of many examples. We don't want to the extent to the extent that we want to be able to say general things about this problem in a general way. Luckily, we have the book by Green, Schwartz, and Witten, which has the last author, and so has given a very beautiful discussion of this problem in a way that anyone, in a way that anyone can understand. Okay, so we will follow that discussion. Okay, so what we're going to do is to characterize anomalies as abstractly, as efficiently as we can. If it's okay with you, Upanu, I'll just continue for 10-15 more minutes till 4 o'clock. Yeah, yeah. We may have to stop the discussion in the middle. Doesn't matter. We'll continue next. Okay. So let us make the follow. I'm going to follow the notation of Green, Schwartz, and Witten in what follows. Okay. So suppose I've got some a symmetry, some general not necessarily abelian symmetry group. Okay. And I've got an infinitesimal symmetry parameter that I'm denoting by lambda. Lambda could have many indices. It could be lambda A. It could be an SU n gauge transformation. And following Green, Schwartz, we will call this quantity. We take the effective action of the theory as a function of the background gauge fields. Okay, so our analysis is going to be abstract. We could have many different background gauge fields. the full set of symmetries is the symmetry group of the theory.
This is the 1 pi effective action.
1 pi effective action. This gamma is a function of all the gauge fields for all possible symmetries that we're interested in.
Lambda is the gauge transformation.
And lambda is the gauge transformation, and this is delta by delta lambda of that. G is a definition.
Log Z.
Yeah, gamma is like log z. Gamma is the effective action, the what we call log z. Path integrate everything else out to get a function of the background gauge fields.
This is equivalent to anomaly function.
This is equivalent to the anomaly function that we are on. Exactly. Okay? And then this Westermino-Witten anomaly condition, okay, can be restated as,
Previous problem, what was this lambda and
so in the previous problem lambda was phi.
oh, phi. Okay. You wanted the coefficient of phi from
Exactly.
Yeah.
Okay?
Is that
Exactly. And the gamma was log z. Okay? Excellent. And now what we do is the following. In general, we expect that this G is going to be an integral over a d-dimensional form. Okay?
What would
Because-
D be determined by?
But
I mean, what would D be determined?
D is the dimension of space-time.
Oh, okay, okay. This is the most general discussion.
This is, I mean, we're just saying that.
space-time discussion.
What?
This is now in space.
Now in space-time. Okay? Now, I'm saying nothing. I'm just saying that anything that is local
Yes. Can be written as
is an integral over a form, local expression. You can write, if you don't want like the form language, you can make star of that form. I'm saying nothing.
So it means that lambda is a zero form.
What?
Lambda is a zero form.
Lambda is a zero form, yes. Lambda is a zero form. It's like phi.
Yes, but more generally,
I thought, yeah, you were considering all possible case terms.
I mean, A is
All possible gauge transformation. We're not talking about higher form symmetries, if that's what you're
I
talking
mean,
about. Yeah. That's well after Green-Schwarz addition. No. By general, I mean like it could be an SUN, it could be a matrix value thing. But it's a function.
a one form.
Yeah. Huh?
A one form. A is a one form.
A is one form, lambda is a zero form.
Yeah.
Okay? Now, note of course that whatever ID is, ID plus d zeta d minus 1 give the same expression for G. So ID is only well defined modulo exact forms. So ID is some D top form. That's obvious. That's just saying that it's an integral over space-time. And because we only care about the integrated version of this quantity, okay? Because we only care about the integrated version of this quantity. By the way, ID of course will also be a function of gauge fields, right? Because we are, I should write it. Okay, we only care about the integrated version of this quantity. Yeah, let's say we're at the moment, let's say we're in a manifold without boundaries. This anomaly, this object, this ID, is only going to be considered up to the ambiguity of adding exact forms. Now, the Westermino consistency condition that we have already considered is this: delta lambda 2 of G of lambda 1 minus delta lambda 1 of G of lambda 2 will be equal to G of lambda, where lambda is equal to lambda 1 actually if I wrote it like this. right? Because first perform lambda 2, then lambda 1, that's lambda 1, lambda 2 minus lambda 2, lambda 1. Okay. Now what we're going to try to do is to find an abstract solution of this equation.
What is the right answer?
See, this is some gauge transformation parameter. Okay.
This is the most general integrability condition.
This is the only integrability condition
I see, okay.
for these anomalies. What we're going to do is to try to find a solution to this integrability condition. Is equal to, no, g of, you see, it was 0 when it was abelian.
I see. Oh, I see. Okay, got it.
When,
Yeah, got it.
okay. Now let's see.
It's like commutator of del lambda 1, del lambda 2 is del lambda while lambda is commutator of lambda 1.
Say that again.
It's commutator of del lambda 1, del lambda 2 is equal to del lambda.
Is the gauge transformation that you get by first doing lambda 1, lambda 2, then doing lambda 2, lambda 1. Right, it's like you rotate this way, then you rotate that way. It's not the same as rotating that way and rotating this way. But the difference between these two rotations is something specific. The Lie algebra, right? Okay, so it's that kind of thing. Of course, it's with function valued things, but it's the same idea. Okay. Now, okay. Now I want to remind you of some things. Okay. First, remember the following. Suppose I have a field strength F, okay, and I do a gauge transformation of F. This transforms like lambda commutator F, because field strengths are in the adjoint of the gauge group. Okay. Next, remember that what does this mean? This means that suppose I take trace F. Sorry. Hello? Hi, Diksha. Thursday is fine. So, Diksha, I'm teaching a class at the moment, so I'm going to have to put down. Sorry. Yeah. Okay, fine. Now let's take f to the power m. Okay, and let's look at its gauge transformation. I'm saying things you know, but I'm just okay. So let's look at the gauge transformation of this quantity. This is going to be, so for instance, let's take trace f squared. Okay, all I'm saying is that this is gauge invariant. You know this, right? Right, because you vary each of them and it cancels and so on. Fine. So trace f to the power m is gauge invariant. This you know. Now, what else? Now something else that is interesting to know is the following. Suppose for a moment we wanted to write, okay, look, okay, consider trace f to the power m. Okay, by f to the power m, what I mean is f wedge f m times. Suppose I consider this object. Okay, now I want to ask, is there an object is there formally, okay, and this is a 2m form. Now I want to ask the following: is there a 2m plus 1 form? is there a, is there a 2m minus 1 form whose gauge variation, no, whose d, is there a 2m minus 1 form, is there some I 2m minus 1 such that d of this is equal to trace f wedge f wedge f? This is the question I'm asking. Okay. Now first let's answer this when this problem is abelian. Okay. When the problem is abelian, this is a very easy question to answer. Because if the problem is abelian, there is
That is with trace or without trace?
this is with trace. Okay, but let me now first look for a moment at the abelian case where there's no trace.
Trace index has nothing to do with this test time index.
Nothing to do. It's just think of it as SUN. It's trace in the SUN matrices.
Yeah.
Okay. Now, it's very easy when this thing is when this one is abelian, because you just replace one of the f's by an a, right? Because you take a wedge f, wedge f, and there are there are m minus 1 of these. Okay, then I take d of this, and because d of each of the f's is 0, the only non-zero quantity is when I get d on a. D on a is equal to f, and we've answered the question. Okay, now more generally, there is always a non-abelian version of this. There is always a non-abelian solution to this problem. We've already seen in the case of in the case of m is equal to 2 how that worked. In the case of m equals 2, what we wanted is a 3 form, which in the abelian case was a wedge f, but in the non-abelian case was a wedge f by minus 2/3 a wedge a. Okay? This quantity was gauge invariant by itself. Okay, that was the non-trivial thing. It was gauge invariant by itself. This quantity in the abelian case is itself gauge invariant, because the usual thing, right? Because it becomes d phi and blah blah blah. But there's a non-abelian version of that, such that d of this whole thing, is f wedge f. Okay, and the way this works is that you see you get a dA from here, and then you get, but dA in the non-abelian case is not by itself.
Yeah, dA plus.
You also need the A commutator A. Okay, you get that from here, but there were 3 such terms. That's why you had the 1/3. This 2 is needed to make it the commutator. Okay, and this algebra you can always play for any m. So there is always a quantity such that its integral is gauge invariant. Okay, so there is always an omega 2m minus 1. So there's always, you can always write I 2m minus 1 as integral omega 2m minus 1. This is nice and gauge invariant, such that it has the property that d of omega 2m minus 1 is equal to f to the m. Such a thing always exists. It's not hard to find. And this thing is called the 2m minus 1, the 2m minus 1th Chern-Simons form, just like a wedge f was a Chern-Simons form. We've seen some of these Chern-Simons forms in.
Is it just a wedge f to the power m minus 1 plus 2 by b a to the power?
I think it might well be that. I would have to check that carefully, but it might well be that. It sounds like it, right?
Yeah.
It sounds like it. It's just that algebra.
Yeah. Just he makes first a f and takes the other term from.
It sounds like it. It sounds like it. Maybe the sign you have to worry about odd, even, or something like that, but more or less that. Okay, great. So, given a polynomial, so why I'm doing this, we'll come to in a moment. So, what we want to do is to solve this consistency condition. Now the logic has taken some sort of leap. Now I'm telling you some apparently unrelated facts. And then we're going to use those apparently unrelated facts to solve that equation. Okay? Fine. So far what have we deduced, or what have we noticed? We found that trace f to the power m can always be written as d omega to the power m minus 2m minus 1, some Chern-Simons form. That there exists such a thing. Moreover, integral omega to the power 2m minus 1 on any m minus 1 dimension, 2m minus 1 dimensional closed manifold is gauge invariant. Okay. Okay. So, consider what we're going to do is this. We're going to try to find a solution for this problem. So, this thing here is some d-dimensional form. What I'm going to do is to parameterize solutions to finding these polynomials that obey this equation. I'm going to parameterize it by d plus 2-dimensional forms. Okay, this is going to be my game. I'm going to find a formal d plus 2-dimensional form that parameterizes solutions to that equation. Okay. Now, given a d plus 2-dimensional form, I have to tell you how I'm going to get my d-dimensional form. So the first step is this. I've got some I d plus 2, for instance, this trace f to the power m, and I will write that I d plus 2 as equal to some d of I d plus 1. In the case that my d plus 1 2-dimensional form was trace f to the power m, I d plus 1 would just be the Chern-Simons form. We will look at, then we will use product rule for such things. What? It's a form with d plus 2 indices. No, where this form lives in some abstract space. What? D was the dimension of our space-time, of our physical problem. Now imagine that you've got some auxiliary d plus 2-dimensional space. We don't care what it is. You know, this is just some formal mathematics for parameterizing solutions. We're going to eventually use it to find some d form.
I mean, why should the form be some exact form?
Why do we need it to be exact? I'm telling you.
Okay, to begin with that. Okay, I see. We want to invent something
that solves this equation?
That's ID plus 2, and we are constructing some ID plus 2.
We're starting with an ID plus 2, and we will use that to find a solution to this equation.
Okay. As of now, we know nothing
we know how that's going to happen, you haven't yet seen.
We are sort of postulating a D plus 2 dimension, D plus 2 exact form.
Exactly. Okay. Now, the next thing we do is the following. Let's look at what the gauge variation delta of I d plus 1 is. D plus 1 is. Okay? We're talking about the local operation now, not the integral. So this I d plus 2 is this local guy, I d plus 1 was this omega. Okay? Now, this Chern-Simons form, we know, is locally not gauge invariant, but its integral was gauge invariant. Therefore, its variation must be d of something. So it must be d of some d-dimensional form ID. Okay? So this ID plus 1 is equal to d of some ID. Okay. Now I want to claim that if G is chosen to be is equal to integral ID, then this will obey all Wess-Zumino-Witten consistency conditions. This is less than 5 minutes to show now, but I think we should just do it next time since we're into your colloquium. Yeah. Okay, at the beginning of next class we will complete this algebra. So what was the descent? We started with the d plus 2 dimensional form. We wrote it as d of something. That something was a d plus 1 dimensional form. Now you cannot take some nice polynomial in f's and write it as d of something made out of f's just because f's have even number of indices. So it has to be something involving a's. You'll never get something locally gauge invariant from there. But we chose that thing, it was always possible, to make it globally gauge invariant. So if you integrated it, it was gauge. Therefore its gauge variation was d of something. Okay, its gauge variation is then d of some d-dimensional form. Okay, and now we're going to show that if you make this choice, if you start with some polynomial involving all the gauge fields, and you generate G by this procedure, then it will automatically obey this condition. It's 2 lines actually. You guys can think about it, but I'll tell you about it next. Okay. The space-time was even dimensional. Exactly. Odd dimensional spacetimes never have any continuous anomalies. They have discrete anomalies.
So this is not just tidal anomaly. I mean, this is
No anomalies of any
kind.
any continuous anomalies.
Any continuous, I see.
Okay, they're full of discrete anomalies. But that's not the discussion we're having here. We're talking about continuous things, right? We're taking gauge fields and field strengths, and these are all infinitesimal notions. Okay, let's complete this next time.